Hello everyone, welcome to Cheenta School of Statistics and Data Science. So for today, we'll be looking at some questions based on calculus from the CMI MSc Data Science entrance of 2020, Part B. That is, the questions are short answer type subjective questions. So this will be the first question that we're looking at, which is the first question of today. That's question number 15 from Part B, which is it says that for the function fx is equal to log x by x, show that the maximum value of y occurs when x equal to e. Okay, use this to show that some inequality that we have. So, usual method of approach for this questions is that when we have been asked to show that the maximum value of um, actually why this is actually fx occurs somewhere, the most standard way is to take the first derivative and then the second derivative and check what happens. So let's take the first derivative here. The first derivative is 1 by x square minus log x by x square. Let's put this way. So when we equate this to 0, we get that log x is 1. That means that x equal to e. So we are here at this point that something is happening at x equal to e. There is some extremum. So we take the double derivative. It turns out to be this expression. So what we do next is substitute x equal to e here. Note that log e is 1. So 1 minus log e is 0. So this term goes to 0. So we're left with minus 1 by e cube. Now e is greater than 0. That means e cube is also greater than 0. That means minus 1 by e cube is less than 0. Thus, f has a global maxima at x equal to e. I hope this much is clear. So the first part is done. So now we have to show the inequality holds. The problem here is that you might think that, okay, we have shown this. So how does the inequality follow from here? So let us first look at what information we have available with us. We know the expression of the function fx. We know the fact that f has a global maximum at x equal to e. So what does this mean? This means that fx is less than is equal to fe for all x is greater than 0. That is that we are working with. So let us use this information and see if we can derive something useful related to the inequality that we have. First, let us calculate the value of fe. So fe is nothing but 1 by e. Why? Log of e is 1 and in the denominator x equal to e. So f of e is nothing but 1 by e. So this means that f of x is less than is equal to f of e for all x positive. So log x by x is less than is equal to 1 by e. Do a cross multiplication and you'll end up with e log x is less than is equal to x. Then, what does this mean? E, since e is multiplied, you can basically take e inside and then this will go to the power of x. This is log x to the power e, still less than x. Now, we can erase both sides as a power of e. So then it becomes e to the power log x whole to the power e less than e to the power x. This thing is a property of logarithm. It says that e log a is a. Right? So this is x to the power e, which is less than e to the power x. This inequality we have achieved, and we know when does it achieve its equality condition. Equality condition is achieved at x equal to e, which is where the global maximum takes place. So this is a very simple question, and you might note that there's a strict inequality here, and we have not got a strict inequality here. We have got less than equal to, and this is okay as long as you mention that does the equality condition hold. So I believe this is kind of an oversight in the question. So you could get marks as long as you write sensibly. So a key takeaway from this question would be that you basically understand how do you approach problems of this kind. That is, if you're asked to check that some function, like check if some function achieves some global maxima, global minima, some place, you go like you just do it for derivative tests that you know. And then if there is something that you prove that you've been asked to prove, most likely you have to use this global maxima, global minima information to prove whatever you have been asked to. In this case, this is an inequality. So we'll move on to the next question. The next question is that Let f be a continuous bijection from a closed unit interval 0 to 1 unto itself. So this means that I'm writing it here. Just one second. Yes, writing it here. This is basically like this. F goes from 0 to 1 to 0 to 1 itself. Note these two keywords. It's continuous and it's a bijection. As a refresher, what does bijection mean? It means the function is both 1, 1, which is called injective, and onto, which is also surjective. So what does this mean? Injective means that fx equal to fy will mean x equal to y, and surjective means that for every y belonging to 0 to 1 here, we'll get x such that fx is y. So just a brief primer on what we will refresh on what bijection was. So let's recall this. This is theorem, which is called the intermediate value theorem. So first, just this digression. In this type of questions, if you're provided with such information about a theorem or something, that means you're more than likely that you have to use it to solve the question. In case this theorem is something that you have not seen before, then read the theorem statement carefully, try to understand what it's trying to say, and then basically you'll have to use this theorem to prove something in the problems. So what is this intermediate value theorem? It says that suppose f is a function, it goes from closed interval a comma b to the set of real numbers, and it is continuous. So it's a real valued function. Suppose c and d are two values in this domain, that is closed interval a comma b, such that fc is less than fd. There is no assumption whether c is less than d or c squared when is equal to d. We don't care about that. Just saying c and d are two numbers such that fc is less than fd. Now take some alpha which lies between fc and fd. Here, take some alpha which lies between fc and fd. Some alpha is an intermediate value. Then this theorem says that there exists y in this a comma b interval such that f of y is alpha, right? Such that f of y is alpha. There is another, there is a bit of intuitive extension that we can do from the way that they have written. That is, you can take this c and d directly to BAB. That is basically says that take any value between fa and fb, then you'll find one point between a and b where f takes that value. So like c and d are not necessarily different from a and b, right? So just graphically, we have to see. Suppose this is a and b, all right, and say this is some function. Okay, wait, I'll just sketch it properly to show graphically what does intermediate value theorem mean for those who have not seen it before. Let's come over here. Consider this is a, this is b. Consider this and say this is some function. This is an example of what IVD is. Right? Suppose, like, so if A is here, if B is here, so let's just mark FA and FB. I said that you can take any intermediate value between FA and FB. Suppose I take this one, this here. Let's see, there exists some point C where it takes that value. This is the crux of the intermediate value theorem, right? Let us look at the first question. Show that f of 0 equals either 0 or 1. So remember that f was a function which is defined as 0 to 1 to itself. It is continuous and it is bijective. We have been asked to show that at 0, f can take either 0 or 1. Now, how do we prove it? Especially, like, always remember that anytime you are faced with such question, that is, show that at this point this function can take this only take this value only, no other value. You should always go for a contradiction. You should always assume that the function takes some other value and try to get a contradiction. Here we have that. Suppose f0 is equal to some c, which is either 0 or 1. Right? Assume that it takes some value c. So basically c is between 0 to 1. I've been given that f and is continuous bijection. We know this. So look at this. There is 0 here. There's c somewhere in between. There's 1 here. Definitely because c is not equal to 0 and 1. So there will be some a between the open interval 0 to c. That is, a is neither 0 nor c. And some b which is between open interval c to 1, neither c and nor 1. Then obviously a is less than c less than b. Right? Since f is bijective, there exists x and y such that fx is a and fy is b. Why? Because the f is bijective, right? So if it's surjective as well. And remember what I said about surjectiveness. I said you take any point in the codomain, there exists another point, some point in the domain such that the function maps at that point to the point in the codomain. So there is an x and y, which basically fx has that fx equal to a and fy equal to b. Now, can we, like, we know that a is not equal to b. Why is that? Because c lies between them. So can we say that x equal to y? Obviously not, because f is injective. Since f is injective, if fx equal to fy would have been true, like fx equal to f like, because also like the question is that, like, can both fx and fy be the same? So it's not right, because fx and fy are different. So obviously x and y are also different. Now you also have that fx is less than fy, and why is that? Because fx is a and fy is b. So fx is less than fy. So I know that c is nothing but an intermediate value which lies between fx and fy, right? C is some intermediate value which lies between fx and fy. So by intermediate value theorem, like we have seen just here in this data in green, there exists some z which will lie between x and y. And this is why I said, notice here they have written that y belongs to AB, and I'm saying that z belongs to xy. That is the sub-interval within the big interval. This is because you can easily take this, like a equal to c and b equal to d. So you don't have to really extend it. So basically, I'm considering the intermediate value theorem within the closed interval x comma y to start with, right? I'm considering intermediate value theorem in x comma y itself. That is why I'm starting here. So don't let it confuse you. Here you're saying that if this is a bigger interval and you're taking a smaller interval within which you're picking that value, you can easily take these two to be the same. The theorem will still hold. So there exists some z here in this interval such that fz is equal to c, right? And there is and here there's a reason. Here there's a reason. Okay, just 1 second. Okay, yeah. So we are beginning again. Yeah. So there's another reason why we took z to be between x and y. We took z to be between x and y because we basically want some contradiction, right? So here between x and y, we're getting that fz is equal to c. Fz is c, but we also know that f0 is c. That is what we started with, right? We started with f0 is c, and 0 lies outside the interval of x and y. 0 does not belong within x comma y. So f0 is c and fz is c. This means that f is not injective, which is a contradiction because we know that f is supposed to be a bijection. So we end up with a contradiction. That means our original assumption was false, and f0 is either 0 or 1. Right? You see where the problem is when we assumed f0 to be c and which is not 0 and 1, because then we can get these two intervals, these two, from which we can pick A and B. If we had not assumed that, if C would have been either 0 or 1, then we wouldn't have gotten these two intervals to pick A and B, so that we can apply intermediate value here and there. The next part is that show that F1 is either 0 or 1. This is exact same as the previous part where we showed F0 is 0 or 1. Proceed absolutely similarly as before. That is, assume that F1 is some C which is neither 0 nor 1. Then you'll get some AB such that A is less than C less than B here. And then again, since F is surjective, we get Fx equal to A and Fy is equal to B. Then again, you'll get some intermediate value between X and Y, right? Difference of X and Y, such that some Z that will be basically F0 is equal to C, and you already had F1 is equal to C. So the same contradiction will come up again. That is not injective. So exactly the way you did part 1, you will be doing part 2. Absolutely same. No difference. The third one is that show that F admits a fixed point. The question is, what is a fixed point? So x0 is a fixed point of F when Fx0 is x0. It is basically Fx equal to x, right? That is when we say Fx equal to x is a fixed point of F. Now, let us start this question and let us get it procedurally. We know that F0 can be 0 or 1, F1 can be again 0 or 1. If F0 equal to 0 and or F1 equal to 1 holds, then we are done, because that is a fixed point, right? Either of them holds, then we're done. That is a fixed point. Also, actually, if you just look at it properly, then if F0 is equal to 0 holds, then F1 has to be 1, because 0 is already taken. So F1 has to be 1. So these two cases will occur together. So when this holds, we are done. So we have to consider the case that this doesn't hold. So consider F0 is equal to 1 and F1 is equal to 0. Note that there's something that you should see, that y is equal to fx is a function we are dealing with, which the point this function will have, the fixed point is the point where it intersects with y equal to x. Because look at this graph, this function can be anything. Y equal to x is here. This is the place where it's x comma x. So we have to basically see where this equals. So keeping that intuition in mind, we can do gx is equal to fx minus x. Then putting the value of 0 and 1, you see that g0 is 1, g1 is minus 1. G is continuous because f is continuous, x is continuous, and g is a difference of two continuous functions, so g is continuous. So we can apply intermediate value theorem. That is, there exists some c which is in the open interval 0 to 1, but gc takes the value 0 because 0 lies between -1 and 1. So there will be some c by intermediate value theorem, but gc is 0. But gc is nothing but fc minus c. So we get fc equal to c, which is, and hence it's proved that we have a fixed point. So here the intuition behind taking gx equal to fx minus x is the fact that this function will have a fixed point where it intersects with the function y equal to x. Keeping that in mind, you can even more easily solve the next part, which is that this asks for example of two functions, one function which is a unique fixed point, one function which is a more than one fixed point. For a unique fixed point, just consider the function 1 minus x. That is, if like just this one, like it is 1 at 0, 0 at 1, comes straight down. This intersects y equal to x is just 1 point, which is half. So a unique fixed point. And for more than one, just take fx equal to x, because this just coincides with y equal to x. It's 0 at 0, 1 1, and it's uncountably many fixed points. So every point is fixed. So again, this is a slightly tougher question than what we have seen till now. It requires some bit of thinking, especially for those who don't know intermediate value theorem, and we'll be seeing it for the first time here. This requires some little bit of brainstorming in order to figure out how to even proceed to apply these theorems. So when you're preparing, there are some theorems like this which hold true for continuous functions and limits. So just just brush them up. Just remember them. Just remember them. How do you approach problems like this? And generally, one of the easiest ways to solve these problems is try to go the way of contradiction. Go the way of contradiction. Especially since you know that you have to use the intermediate value theorem, try to cook up some contradiction which uses the intermediate value theorem and try to arrive there. So it's kind of like a back calculation, but okay, get it. Like it's a being to the proceed. And this is another trick that you have learned is that take the difference of two functions if you want to show some relation between them, whether they're equal, whether they're greater than, less than. Take the difference and see what happens with that. Right. So this would be all for today. And thank you for watching. And I'll see you in the next video.